Welcome back everyone to another video in our FE Civil Preparation course. In this video, we are going to learn about torsion stress. So what is torsion? Torsion is the twisting of an object by a moment acting about the object's longitudinal axis, and this moment is known as torque. If we have a circular shaft, as we can see here, fixed from the point A and free from the point B, and we applied a torsion moment at the end, the circular beam will start to twist as we can see here, and the line of AB will start to get deformed from the original direction, which is dotted here, to the current location, causing an angle of twist. In our next video, we will talk in details about the torsion strain and its calculations. However, in this video we will focus on the torsion stress. Torsion moment on an object causes shear stress. That's why torsion stresses were considered to be one of the indirect stresses. It is worth mentioning that in our course we will be dealing only with circular sections when it comes to torsion stress. Shear stress due to torsion could be calculated using the following formula. Tau equals T multiplied by R over J, where T is the torsion moment, R is the radius of the cross section, and G is the polar moment of inertia. So what is the polar moment of inertia? Polar moment of inertia is the section property that defines the section's resistance to torsion moment due to its shape. From the equation of the shear stress, we can find that it is relevant to R, which is the distance between the center of the cross section and the location where we want to calculate the stress, which means the torsion stress will equal to 0 at the center if you used R to equal 0, and it will be maximum value when R is the radius of the cross section. Based on that, we can conclude that the shear stress distribution inside the section under torsion moment looks like this. It starts with 0 and it increases till it reaches the maximum value at the section surface of the section. This distribution applies to solid and to hollow sections with thick walls. We will discuss in our next videos how to deal with thin-walled sections. And this is why using a hollow section could be very efficient for the elements mainly under torques, because the torque is mainly resisted by the outer surface and the core of the section resists only a very small portion of the torsion stress. So now, let's have an example of this.
So let's check this example. We have a solid steel shaft here of 200 mm diameter, and we have torque of 135.6 kN, and we want to calculate the maximum shear stress in this shaft. Okay, this is a direct example, so let's state the known. We have R of 100 mm because we have the diameter of 200 mm. We have the torsion, it is 135.6 kN meter, and we know that tau, which is the shear stress due to the torsion moment, equals T multiplied by R over J. We can get J from the reference handbook. As I told you, it's already available there, and I will show you in the last lecture in this course how to use the reference handbook. But now I will tell you the equation for it directly. It is pi R power 4 over 2. So solving this equation, we'll get that J equals 1.58 multiplied by 10 power 8 millimeter power 4. So we can calculate that tau now equals 135.6, which is the torsion, but it is per kilonewton meter, so we will multiply by 1000 because we want it to be per only newton, and again we will multiply by another 1000 because we want it to be per millimeter. So we multiply the 135.6 by 1000, again by 1000, so instead of being kilonewton meter to be newton millimeter. Then we multiply again by 100, which is the R, and of course the R is per millimeter already, so we don't need to multiply by anything. This will be over the J, which is 1.58 multiplied by 10 power 8. Solving this equation, you will get that tau equals 85.5 Newton per millimeter square, which is the same as megapascal. So this is it for our video today. Thank you.